Today we're at Octane Alley in North Geelong and we're with Tyrone and we're going to run through this really cool old school Buick. For Australian viewers, they've probably never seen this engine before, but it's actually called a Stage II.
Yeah, it's called a Buick Stage II. It was run by the Buick Motorsport group in the early 80s. The Stage II engine family the block was a dry sump based block, mainly based for drag racing and for an Indycar program starting in '84. So they're an iron block, dry sumped, very high flowing heads, Siamese bores, and they were nominally a 4.1 litre, so Buick engine. But for the Indycar introduced a stock block class where you could run a 3.3 to 3.4 litre. You were limited to 55 inches of mercury for boost. So for everyone, that's about 17 pounds.
Is that sort of a bit like our Group A
Absolutely,
racing, where they had to make
very much. Yep. So traditionally, Indycar engines were a bespoke custom race engine, usually by Cosworth or Chevy Ilmore, which was from the UK, and they were 2.65 litre and 44 inches of mercury, which is about 12 pounds of boost. But for the stock block, they allowed them to run 17 pounds of boost and only 3.3 or 3.4 litres, 2 valve per cylinder, to try and encourage domestic US manufacturers.
So people might remember the Grand National.
Yeah,
that was
the G&X.
Very cool car. So this was in a limited version?
Yeah, limited version. So the Stage 2 block was available as like a limited production option, like the old Chevy COPO option. So you could order like a stripped down drag car with a Stage 2 block in it, and essentially to get it homologated for Indycar, to be a stock block, to get it homologated for NHRA, and also for, they used to run them in Indy lights as a 4.1 litre, single 4-barrel, 550 horsepower screamer. For like, essentially it's like the tier 2 level of the IndyCar series. So they're all like a one make, sort of all Buick engine.
So this particular engine, I think, is it circa 1984?
This is a 1984 spec engine from the AJ Foyt team, so it ran in 1984.
So this specific engine was in an Indycar?
Yes, this would have been one of the, I think there was about 50 engines it's rotated through the team. Like it was quite a big budget sort of operation back then. It ran if you're familiar with GM, it's pre-3800. So there's three families of V6.
People obviously think, when they think Buick V6 in Australia,
they think Commodore.
They think V and Commodore.
Yeah.
The burnout engine.
Yeah, that's right. That's called the 3800. So that came out in about 86 in North America, 88 or 89 for us, where VNs came out. That was sort of like a re-engineered engine, balance shafts and all that sort of stuff. So this is what's called a pre-3800. It's what's called an on-centre engine. So back in the day, this is a Rover V8 with 2 cylinders cut off and an iron block.
I've actually heard that before, yeah.
So the Buick 215 V8 was introduced. All aluminium. The casting scrap rates were quite difficult. It's a very expensive engine to make. They on-sold it to Rover because they were shopping for a V8 for the Range Rover at the time, and MGB V8. Buick then built an iron block alloy headed version, a 300 cuber. Because of the bigger is better ethos in the 1970s, essentially those little engines got forgotten. Come the fuel crisis in 73, 74, GM then introduced this engine as a V6. They introduced the 215 cube, cut 2 cylinders off it, and made a V6 out of all iron because it was cheap. We step forward to 1984, the stock block. They were predicting like a 600 horsepower, 650 horsepower platform being like a subclass.
Yeah.
Because the Ilmores are up around 900 horsepower from 2.65 litres. But the stock block class ended up being 850 at 8.5, and Buick were very dominant in the category. So originally this engine would have been built with a VN type coil packs. The 3+1 tooth on the balancer, it had like an old ECU called like a pizza box. It was just pre-808 GM VN Commodore ECU.
And it would have run on methanol?
All Indycars run on methanol. So just for a safety aspect, so that methanol's not as combustible when it spills like gasoline is, but it's also hard to see the fire. Yeah, so it was run on methanol and large injectors, and 1984, you think Cordia turbo type technology, and that was state of the art. And they were making the very expensive valve train, all custom made Jessel shaft mounted rockers, and
these had titanium
valves made by Del West, and a rev kit had roller followers back in 1984 on the camshaft, and it had a little rev kit which is like a set of springs on top of the cam follower to take the load off the valve springs. Like the valve springs that are in it are quite strong as well, but valve spring technology is not like it is today with elliptical wire and all that sort of stuff. Back then, they had to do everything they could to try and control the valve train for a pushrod engine with I think it's about a 2.15 inch inlet valve. Even though it was titanium, 8,500 RPM is phenomenal. That's where peak power was, and they used to run them to 9.5.
So what sort of turbocharger were they running back then?
Back in the day, it's a large diesel style turbocharger, a big old style Garrett with a big old external. You may have seen the pictures of the Indy cars with a big old external, had a canister like this on it, an external gate, big single scroll turbo, because the target RPM was really 7,500 to 9,500. They really didn't make boost to 6.5. If they were building an Indy car of this performance today, they would use something like a 4088 or a EFR 8374, and it would be probably 2/3 the inertia, 3 times the spool, and it would be half the size, in terms of physical dimensions. We've sort of got involved with the project, and we selected a whole set HX40. Part of that was based on the customer's budget. I sort of parameterized what sort of performance we needed, what we were looking for. We were sort of targeting around 700 and a bit, because it's an open sports sedan, so it has a 6-litre capacity limit, which is 1.7 times multiplication for turbo, which gets us back to, we can't be any bigger than 3.4 litres, so we're a fraction over 3.3.
So we're going to run this up in a minute, but we're not going to be spinning this to 8.5, are we?
No. In the interest of longevity, because of the pedigree and heritage of the engine, like the blocks, pretty much irreplaceable to buy a new one. One with a hole in it is about $3,000 US in the to one that's been repaired.
Yeah, if you can find one.
Yeah, and the valve train inertia goes up with the cube of speed, like so the valve train loads because of all the extra inertia and all that sort of stuff. So boost has killed far less engines than high RPM inertial loads. So the RPM limit will be around 7.5, and I've targeted the power curve to be around sort of peak powers between 6 and 6.5, and just flattens out to 7, and then we just roll it off so that the customer doesn't want to rev it to the limit. And in the interest of longevity, like this valve train will last a long time at 7,500 RPM, but at 8,500 RPM, you'd probably do a season of sports sedan racing, which is 6 rounds, 7 rounds, and you'd be putting springs, valves, collets, retainers in, and that's a very expensive exercise, which 1,000 RPM, it doesn't justify it. And like we're 100 horsepower down from what they were at the peak of Indycar, and they would have.
And this has got to do far more.
It's got to do a lot more miles. Like they would have done 600 miles between teardowns, and that would have been a full top end replacement, valves, collets, all that sort of stuff. We're sort of thinking that we're 100 horsepower down on its heyday, but we've got probably 8 times the life. So
much more usable torque.
Oh yeah, much bigger spread. Like we're on boost at 3. Like we've got about between sort of 8 and 10 at $3,000 steady state, and all the way up to like $7,000. We can sort of make 28 if we need to, but to get the power target, and we've got to sort of consider the gearbox in the vehicle as well. So we're sort of pegged at 900 Newton meters. We also do not exceed at any point, because that's pretty much what the limit of the gearbox and driveline is. So yeah, if we say 750 and 870 Newton meters, that's pretty much where we've ended up. And the torque is very flat, so probably from 4 to 6.5, probably 6. The torque's almost constant. So
one thing you've really changed, it's not really that noticeable if you don't know what you're looking at, but this is all drive-by-wire now.
That's exactly right.
This is the actual original manifold. You've just modified it.
So essentially, in an Indy car, these headers used to point back the other way. So we've taken the left header and the right header, swapped them round, and there's been a little bit of change here at the V-band end, but the turbo used to sit at the back of the gearbox and then discharge straight into the throttle inlet, which was originally the other way around. Now, they never used to run an intercooler because they were on methanol and they only had 17 pounds of boost, so back in the day that wasn't deemed necessary. We've turned the manifold around to suit the package. This is mid-mount in a Torana, so in line with the front of the engine is about the base of the windscreen.
So this is going into a sports sedan?
Yeah, 1,100 kilos with driver, 1,125 with driver.
So the engine sort of sits next to the driver?
Pretty much, yeah. So he's going to have a warm leg, so all this has to be HPC coated on the other side. One of the things for going forward with this build was absolute reliability. We don't want to be working on it all the time. It's got to be robust. Things like distributors and all that sort of stuff need attention. Serviceability isn't easy in the vehicle. Like, it is, but you've got to do a lot of work to get access to it. As you can see, it's all dry sump. That's all original. It's a new pump, but the pump is the same manufacturer.
And that fuel rail is actually, that's original, isn't it?
Yeah, and that fuel rail is 1 mil stainless, and it's TIG welded here. So there's all these beautiful clamps. The injectors, this is a cast magnesium. This whole manifold weighs about 3.5 kilos, and it's all cast magnesium. Inside the manifold are a series of hand-formed, they got cast bosses and they're hand-formed trumpets. It's a shame we sort of should have been a bit more prepared to be able to show you inside. It's an absolute work of art inside, just how it was done in that analog era. Nowadays it'd be done with CNC or there'd be some sort of 3D printing.
And you're running everything through a Motec M1
Yeah, we're
series.
using a Motec M1, yeah. So we're using a GPA package. The GPA package is required because as a sports sedan, you're not allowed to run traction control and launch control. A GPR package has that in there. We want to be squeaky clean because the car's very, very quick, and to remove any doubt if we're using traction control or anything like that, because drive-by-wire almost gives you the control that traction control will do if the driver's sensible with the throttle.
Well, why don't we give it a run up on the dyno and let's hear what this thing sounds like.
Excellent. So on the min boost, we made 480 horsepower.
Okay.
You can see the tightness of the boost control, and that's just with a single 3-port valve. We'll just now go to 40% of total boost. But the good thing about an M1 is you've got all this live graph. You can pause it, and it's just like having i2 rather than having to download the logging. We've got all the live stuff. You can just scroll back and forth. We can scroll back to our run. A few minutes ago now. There we go. So there's our run. We can go back and make a few changes, and then we can just F6 back to the main screen, and away we go. We're live again. This curve is governed by the physics of the turbo and its compressor map, and then we just essentially increase to the next level. And we walk up the boost. And then here the torque is an exact mirror of the other torque, just being scaled up by the amount of boost. We shape how it comes on to boost so that it's not such a sudden transition, and you can see no matter which boost level you're at, the transition's the same. So for the driver to be able to drive it, it feels the same no matter which pedal position he's at, you know. So because that's just from my racing experience, I think that makes the car very easy to drive, and from an OE road car, performance road car thing, makes them much more manageable.
Why don't you give us a run through some of the stuff that the Motec's controlling, I guess. Some of the sensors and stuff on the
Yeah. All right. Well, because of the, you can see the injectors, they fit down into the trumpet. We've had to stick with the older style injectors because the manifold, the customer didn't want to modify the historic manifold. So
that's understandable.
Yeah, because it does have a lot of pedigree. So we've gone with the original injectors. They're about 11 inches from the back of the valve, so it's sort of like supercar type material.
Dumb question. Why couldn't you run a newer injector in that position?
Normally injectors are sealed in the rail at the top like these ones are, and then at the bottom by the bottom O-ring. These injectors are the large EV1 style with a round circular body, steel body, and that's how they seal. They got custom seals that are retained in the actual casting of the top half of the manifold.
So they are like the old Mitsubishi ones that used to sit on.
That's right. That used to sit down in and held in with a rubber O-ring.
Rubber O-ring. They always leaked.
Yeah, there's nothing for the injector to sit down into the runner, so that we would have to modify. We'd probably have to modify the injector because all the modern EV6, EV14 style injectors, most of them are non-circular. We would have to probably get some 3D printed bushes to sort of adapt them to that size, and we'd have to find some way of sealing them in the bottom. So the decision was made, well, if these injectors come up all right, we had them characterised at Motec so we could use them with the M1, because the M1 fuel model is very, very accurate, OE type accuracy, the way it models the air coming into the engine and then delivers the appropriate amount of fuel. It's the only negative of that, or the only caveat to that, is that the injector has to be accurately calibrated. So they're an old peak and hold style injector. They're 6 amps to open them and about 2.5 amps to keep them held. So they're pretty old school. They're not super fast, but they flow 1870 cc's at 3 bar. So one injector flows as much as 6 BA turbo injectors at the same pressure. So, because it was originally a methanol engine, right? Yeah. So methanol needs 2.5 times by volume.
So it's perfect now to run it on E85.
That's exactly, you're thinking exactly the way we thought. So E85 allows us to run the engine at its optimum performance. We can be quite safe away from knock. There's no category limitation of being able to run E85. So when there's no rules that prevent you from running it for a race engine, there's no reason why you wouldn't. So the Motec controls the drive-by-wire. The M1, we've gone drive-by-wire to give improved drivability. With the injectors so high mounted, with an Indycar, that didn't matter because there wasn't much transient. It was just almost constant speed all the way around. With this, it's like a supercar, so it's a lot of challenge to get the good fuel control transiently. So the Motec M1 is the first ECU to be able to have what's called a fuel film model. Essentially, it models the puddle of fuel that exists at all times in the intake runner, from the wetted walls and on the back of the valve, any little recesses where the manifold joins the head. OE ECUs have been using this probably from around the late 90s. It started to become popular, and sort of by the mid 2000s it was standard. The fuel film modelling the growth and decay of the size of the puddle is how transient fuel's done. So without an M1, it would be very difficult to get the good drivability that this has got. Like, we can snap the throttle open as if the injectors were pointing at the back of the valve. Okay. Yeah. So it's quite good like that. We're very, very happy with how it's came up. I was concerned at the start.
I was wondering the same thing, because it's so far from... these sorts of setups, essentially like, mounting a carby up
very high.
Very
the
high
transient
to get
fuel is the problem. Because, as I often say to people when they talk about tuning, like, the peak power number on a naturally aspirated engine might be 5% of the total dyno time. For a turbo engine, you might say 10% because you've got to dial in a bit of boost control. It's the transient fuel and the drivability that makes the difference between a good race engine and something that the driver's got to drive around. And the driver it should be intuitive. So managing this sort of stuff, and I think if you talk to any supercar team, the improvement over an M800, which is what they used to run, compared to a fuel film model, once it's a little bit more time consuming to calibrate, but to get a really good result, the total time is less. It's probably a steeper initial learning curve, but if you're looking at all petrol engines with all similar injector distances, you could almost use the one cal and cheating a few times, I've probably done that, save a bit of time. But with something like this, it's absolutely a unique cal for the age of and the spray pattern of the injectors, not as well developed as modern injectors, but it's a good result. We're quite happy. I did actually think at the start when we got underway that I would be changing injectors, but we've saved the customer a significant cost and without having to modify his manifold, and so win-win. We've gone to the LS coils, as I've spoken about earlier. That's all controlled by the Motec. We have coolant temp in the back of the head. We have a Bosch T-map, being like sort of state-of-the-art for intake air pressure, like manifold pressure, intake air temperature. We run a boost pressure sensor also pre the throttle to do the boost control. That gives you a much better control input into your boost control, so that what happens is when you close the throttle and open the throttle again, you can be targeting the upstream pressure, and you can maintain a delta pressure across the throttle, so you've got a better range of authority for your boost control. We're also measuring oil temp, oil pressure, fuel pressure. We're measuring turbo speed, compressor inlet temperature and pressure, compressor outlet temperature and pressure, exhaust turbine inlet pressure, exhaust turbine inlet temperature. We've got individual thermocouples on the exhaust port runners. We've got the lambda to CAN, so it's an inbuilt LSU 4.9 controller that spits, so it doesn't use up analog input pins on the ECU. It's just a direct CAN message between the ECU and the lambda, and what that does, it sends all the error messages, and it's just plug and play. It's self-calibrating, no air cal, any of that sort of stuff. So the customer wants to change the O2 sensor, because LSUs in turbo E85 environments, high temperatures all the time, they're probably not as robust as the NTK sensor, but they're much faster, they read better lean, and they've got a bit better full rich capability. So I tend to stick with the LSUs. It's the newest technology. It's also good bang for the buck. An NTK is probably $280 for the sensor, and these are like $125, $130. So once again, it's just trying to get the value. I don't mind spending or directing the customer to spend the money, but is that gain going to be quantifiable? Is it worth paying double the money for a consumable oxygen sensor for very little gain? So
unlike standard, I see you're running a PWR barrel intercooler, water intercooler over there.
Yeah, so we're running the water to air.
I guess you've got the room to run it. So
we've got the room to run it. The car's got like an acre of room inside at the front. So I with enough water capacity, like the intake temperature's like easy to manage. We do have the option of an air-to-air intercooler in the car, very large air-to-air cooler. We've gone with the barrel because just from a packaging point of view, the total amount of plumbing, a bit of weight saving. Admittedly though, 1 litre of water is 1 kilo, so I'm sort of dubious whether the weight saving is fully realised. We're also running dual wastegate, dual MVS 38mm TL wastegates. I've done the calculation. I expected at peak power probably 40% of the total flow would be going through the wastegates, because the turbo is probably, honestly, probably 780 horsepower turbo, maybe 800 if you pushed it a little bit hard. We expected to be 700 plus, so I knew that at peak power, a lot of the exhaust flow would have to be wastegated. So yeah, typically it's about 40%. So each side of the engine's 1.7 litres. From my experience, the MVS is quite an efficient wastegate at that sort of, so you sort of think of a 400 horsepower power level. We can wind the boost back. I've got the min boost, like what I call min boost, but the base spring value is 4.5 pounds.
That's not even boost.
That's not even boost, that's right. But the idea is, like, this car is 1,100 kilos, 1,125 kilos. It's got not much mass to try and assist the traction. It's got very large tyres, so in the wet it can be quite a handful. So being able to manage the minimum boost and control the torque. I come from an OE background, so my thinking is the min boost should be as low as possible, and that gives me more headroom to play with, how much boost control I can dial up.
Yeah, we see plenty of high-powered street cars and minimum boost is 20 plus.
Yeah,
and they're quite undrivable.
That's right, and that people, I think, lose sight of the fact that it's very easy to make a lot of performance, but it's very hard to scale that performance back when you're at part throttle. And so the two MVSs, we use just a single Mac valve to control both of them. There's one in each scroll because we've gone to a twin scroll setup. I modified the original Y-piece to be twin scroll, just put a tongue inside. It's a bit of stuffing around, to be perfectly honest. It took way longer than we thought, but it's the outcome. Like we did run this turbo with the existing manifold, like a twin scroll turbo, but with a single scroll manifold. And we picked up about 1,000 RPM of boost response. So we had sort of boost, usable boost. When I say min boost, I sort of mean usable boost at $3,000, whereas when we first set it up without the tongue in the manifold, it was really $4,000. And I was sort of, given that our top end rev range for durability we wanted to keep below 7, it didn't give the customer a usable rev range. So my idea is the car's got to have good performance. It's got to be extremely robust. It's got to have good drivability. Part of that good drivability is a usable rev range, because all too often people think of race engines just being top end, but that's not always the case. So.
Yeah, and this is a bit different to the Indy car, like you touched on earlier. It's just singing the whole time.
That's right. It's just going.
It's not really using mid range.
Yeah, 40% throttle and 100% throttle, but it's only going between 7.5 and 9.5. And it spends a lot of time around 8.5. One of the other things we've done to the engine as well is replace the old 3+1 Delco style pickup. We've used a OE style tone wheel. It's actually a 5.4 Boss engine tone wheel, because they're quite cheap. They're a very effective tone wheel. And we've used a FG Falcon crank trigger. Now, the reason I tend to do that is, rather than using laser cut tone wheels, which can have like 1 or 2 degrees error for each of the teeth, using an OE setup like this, the material has got the right magnetic properties, and OE variable reluctance sensors, or MAG sensors as a lot of people call them, are very, very durable. They very rarely suffer from heat like Hall effect. You've got to get the trigger levels correct for going through the RPM range for the right voltage trigger level, and the M1's got a digital signal processor inside the input stage for the crank trigger, or the universal digital inputs. So there's 12 digital inputs for cam and all that sort of stuff. But this will sync up at less than 100 RPM. It has no missed teeth or anything like that. And a lot of people have a lot of problems. I settle on a lot of race cars where engines misfire at high RPM and the timing jumps around. Like this is within 0.5 of a degree from 1,000 RPM to 7,000. So that timing accuracy is very important when you've got a highly boosted engine, something that's, you want to be able to run it as, you don't want to have to come back 2 or 4 degrees from optimum because you've got 2 degrees of spark scatter. So having a good trigger system, I can't stress enough how important that is. If all those things are right, your tune is much easier.
Is the engine itself at the bottom end? Is it still how it was?
The crank is a LA billet crank, so Moldex and LA billet were the original suppliers. The crank's the same. The conrods are exact replacements, like new replacements of the existing Carrillos. The CP pistons are a copy of the existing pistons, so we couldn't get the original pistons, but we've got a CP copy. It's custom made. The rocker gear is all Jessel. The heads are all the Buick Motorsport castings. The manifolds, exactly the same. The dry sump pump's exactly the same, made by the same company, but it's just a new one because the old one has probably seen better days. And we're trying to do the right thing. Oil system's very important. All the most of the plumbing, believe it or not, is the fuel rails all original. The sumps original. All the valves on the bottom, like the one-way valves and screens, they're all original. So pretty much it's all Indy. The rocker covers are exactly, they have not been touched. So they are exactly the same. I assume then. Yeah, they're exactly the same. I wanted to touch them up and give them a bit of a birthday, but the other one's got a little bit of black paint off it. Just that's a bit of patina from the era, but that's exactly how they used to paint them. So being a stage motor, a lot of stuff is similar to a pre-3800 Buick, but a lot of stuff is also just different enough to be right pain. So for instance, the gear drive, when we first built the engine, we couldn't get another gear drive. The gear drive looked okay, there's a bit of wear on the teeth, we thought we'll run it again. We did a bit of an engine break-in, and I'm sort of quite sensitive, tuned in to like just listening to engine noises, and we did a bit of work. I think we started making 10 or 12 pounds of boost, and then the engine was sort of a little bit off song. It was going tick, 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 and it was a different frequency to what you would expect half engine speed of one of the valves to be, and it actually turned out to be the idler gear on the gear drive had a crack between the root of the tooth and the inner bore where the needle rollers run, and every time it would go over a cam lobe it was opening up like that, and we were very lucky with that. It could have been quite catastrophic, but I suppose it comes back to like something like this that has like historic significance. It's unknown history, like the parts are all very good quality. It's all Millerton, it was all custom made by Millerton. We got in contact with Millerton, they couldn't supply one, they hadn't made one since early 2000s. Yeah. They've had none on the shelf.
But at the end of the day, you're using a 35-year-old engine.
That's right, and that's what you've got to be aware of as well. You've got to be very careful, like it's irreplaceable, right? Like it's almost irreplaceable, certainly not for reasonable money. Yeah, so it took time. So that was 6 months ago, like just before 6 months expired just before Christmas. So in the middle of the year last year, we're all set to do it. I sort of blanked out a month of just my time because just sort of trying to fit it around other jobs and to focus on the job, and we couldn't get a gear drive. So Millerton were actually awesome in the US. They rang around all their suppliers, these little places in Kentucky and North Carolina where there's a lot of Indycar teams, and they found someone who used to do a bit of work on Indy engines, and we were able to get the last brand new packaged Millerton gear drive for a Stage II. So that was like, it was unbelievable. And we're thinking, we're going to have to, Paul, the owner, would have to give up his firstborn, but it actually wasn't about, I think it was about $1,200 landed. So when you think, gear drives typically $700 or $800 for a generic V8, it was quite surprising sometimes. But yeah, so little things like that like come as an obstacle. So, I'm quite confident this engine's got pretty much everything new. The only thing we couldn't replace were the roller followers, but we've got a large supply that we could choose from. We crack tested them, and then speaking to Iski, the problem is the needle rollers. So if there's no spalling in there, well, they're good to go. The rockers also Jessel, they're all custom. You've got to buy like 3 or 4 sets to get one. So not slightly economically challenging. So, but once again, they're all in really good condition. It's got new push rods, so pretty much everything that we need to do on the engine to confidently run it at sort of state and national level sports sedans is been done. So we wouldn't sort of do something that's on the edge, because a $30 or $100 part could destroy this engine.
Yeah,
so.
right.
But it's not a no expense rebuild either. Like there's been, once again, that focus on value rather than the absolute cost. What's the best value we get out of doing this?